This I got from a textbook a while back. I don't know if it was, properly vetted information. Right? It could be legit. I'm not sure. Are violent crimes distributed uniformly? Based on data from FBI, violent crimes in a recent year occurred with a distribution given in the accompanying table. Violent crimes include a murder, non-negligent manslaughter, a word I never like to say, robbery, and aggravated assault. The listed percentages are based on a total of that number of cases. Use a .01 to test the claim that violent crimes are distributed equally among the 12 months. All right, so not equally among the categories of violent crime. That's another question I suppose we could ask, but I mean there is data to suggest that more violent crimes occur during the summer months. So is this an example of that? Who knows, right? And then follow up stuff. Now, if it's uniform, so these are our observed percentages. The expected percentages should be, well, it should be the same number per category. So it should be 1/12 of the available 100%, right? So if I do 100 divided by the 12 months, I should have 8 1/3% each month. So I'll just say 8 1/3.
Can you do 3 with a dash over it?
You sure could.
Can you do 25/3?
You could, yeah, I suppose.
Pretty strong.
I'm gonna do 25.
All right, so these are what the percentages should be.
You can't
Yeah.
just do like dot with it.
For the AP, no, because we need to fake that we're doing these calculations, and it is a one-to-one relationship between observed and expected. So technically, we would have to, if we were doing this in a spreadsheet, we'd have to subtract 8 1/3 from each one of those observed values. All right, but before we get too far along that pathway, let me state the null and alternative hypotheses, HOHA. So this could be pretty complicated. We have January through December. I'm gonna let January be month 1, 2, 3, and so on, all the way through December.
Is this a leap year?
This year is not.
No, this.
Oh, I don't know. We always assume it's not.
Probably not.
Well, 25% of the time it's gonna be.
It sure is.
Stats guy.
Well, 25% of the number of years it's gonna be. Yeah, time could mean so many things. So, population proportion if it's uniform, all these population proportions should be the same. So, population proportion for group 1 should be the same as 2, should be the same as 3, should be the same as, now we can go ...
There we go.
all the way up to population proportion for 12. All right.
Wait, so they'll accept that?
Yeah, this is properly formatted.
There we go.
So at least 1p is not equal. All right. Now, for a chi-square test, and this is anytime you have a one-way table and you're testing a claim about proportions, you're working with a chi-square distribution. All right. Now, the chi-square distribution, like a t-distribution, has degrees of freedom. So degrees of freedom is equal to k minus 1, where k is the number of categories.
K for category.
Exactly. That's what I was thinking.
In German.
In German, yes.
You ready for the speeches today?
We don't say n minus 1, because n represents, if you think about a sample proportion, every one of these months is the result of a calculation related to sample proportion, which is x over n. N is the number of items in a sample, and we have 12 samples here. So, but that n has already been accounted for, so I can't use it again. What some people do is they go with a capital N to represent the number of samples and lowercase n to represent the number within each sample. That's something you could do too. As long as it's obvious what calculation you're doing, they don't really get too bent out of shape over that. So degrees of freedom would be 12 minus 1, or 11. And it's 12 because we're looking at each month as being a category. All right. Now, a chi-square distribution is always right skewed and non-negative
Why is that?
for reasons that we will get to.
Now I remember that's opposite too. Right is actually on the left.
Yeah, bulk of the data on the left, tail on the right, right skew. All right, the center of the hump, oh, that's weird. The center of that hump is whatever your degrees of freedom value is. So it starts off at 0, it goes off to positive infinity. We're gonna have a critical value for chi-square, which we have to actually get from the tables. All right, because to the best of my knowledge, the numworks calculator doesn't have, in the probability distributions menu, it gives you T, Z, Poisson, but it doesn't give you chi-square. All right, so we'll have to get that. The alpha value still corresponds to the shaded area. They said alpha is equal to 0.01. All right, so we need our test statistic. So our test statistic, chi-square. All right, so it's not an x squared, it's a chi-square, it's just notation. Because I've had people in the past, they do all these computations and they go to take the square root of it later on to solve for x. That's not the case here.
The alpha is the rejection region, right?
It corresponds with the rejection region, yep.
What is chi?
Because I think that was mixed
Chi
up
is
on
a
the
Greek
quizzes.
letter. Huh?
I think that was mixed up on the quizzes because I think it said the critical value was rejection region.
Is that the one with the matching?
Yeah.
Yeah, that's the one I had a typo in it.
And also the one with you had to put in the answer.
That one I don't know about, but I'll take a look. Excuse me. Wrong pipe there. So O minus E squared divided by E. That's going to give us our test statistic. Now we do have to show evidence of a substitution. All right, so we're not actually going to do the math, but we're going to kind of make it seem like we are. All right. Like students paying attention in class. You're not always doing it, you just try to make it seem like you are. All right, so I'm going to do 7.7 minus 8 1/3 squared over 8 1/3. And I'm going to do basically the first two and the last one. And we're going to go dot, dot, dot. All right, so the next one is 7.4. So it's got the same ingredients, except the first term there is going to be 7.4. Plus, then we do it again, but this time a dot, 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 and we just go right to the last one, which is 7.7, which is kind of convenient.
Good for you.
Oh yeah, sorry about that. Yeah, absolutely. Convenient only for me. See how easy that was? So then, instead of actually computing all of these values, because I mean, just because we wrote 3 of them doesn't mean that there's only 3 of them. Because the other 9 to worry about. So I'll use the app, the inference app. We go to test, chi-square. The first option is goodness of fit. Right? So we're trying to determine whether the array of data that we have is going to be a good fit for a uniform distribution. Right? So if it is, then we can assume, since the uniform distribution has equal probabilities, we could then assume that our sampling distribution has roughly equal values, which corresponds to the population level. All right. So I hit OK, I type in the numbers. This is from a different problem, so I gotta overwrite it. Bless you, bless you. So 7.7, 7.4. Now technically these are supposed to be counts. And when you talk about counts, it should be whole number values. But the number of cases, 1.4 million or so. I'll just kind of give you the short version of it. The larger the population that you're working with, or larger the samples, the sample of samples, the less effective the chi-square is. Because if you have a large enough sample size, the null hypothesis is going to reject even when there isn't when there isn't significance involved. Right? So sometimes we convert to percents or decimals, even though these are emblematic of counts. Right? So you just got to kind of look at it critically. Oh, that's just a 9. 8.9, 8.6, and 8.7.
So you put everything as 25 over 3?
Yeah. I don't think, because I don't think you can do a like a rule in this app. Yeah. Hate when that happens. Oh, I went too far. Shift, copy. Yeah, so I'm just gonna paste it on down the line. Let's see if it, it doesn't let me
paste it there?
Yeah. I mean, I gotta do it individually, but still better than typing it every time. All right, so I have my values in. I must have missed. Oh yeah, I didn't go all the way. Like there's only 9 degrees of freedom. That's not true, because I forgot November and December. All right, so confirmed degrees of freedom is 11. It automatically gives you that, which is nice. Right. 0.01, I had that from a previous problem, otherwise you overwrite it. Go to next, it gives you the chi-square, so that's the test statistic, about 0.481. The p-value is the probability that the test statistic, or that chi-square, force of habit, is greater than whatever the test statistic was, 0.481, and that's 0.999. I'm gonna go a bunch of decimal places because otherwise it overrounds. So 6 9s and then an 8 9. And when you get a p-value that's this big, it essentially means that you really had no business doing the hypothesis test to begin with, right? Because this is saying that there was never even a chance that you would be able to reject the null hypothesis. All right, so this is telling us that the HO is a keeper. Ditch the alternative.
But isn't that like not the case? Like
In
okay.
real life, no.
No, because they're all different.
They are all different, but what it's saying is this enough information to conclude that on the population level, that they're significantly enough different?
Substantially.
Exactly. All right, so there is insufficient evidence to reject the claim. Of the null hypothesis, I really don't want to state that the insufficient evidence to reject the claim that the population proportion for January is the same as the population proportion for February, for March, for April, and so on. So I'm going to kind of paraphrase and say of no difference in population proportions
Of violent crimes.
violent crimes.
From January to December.
Yep. At the .01 level, significance level. Now we want to answer the question, is there a reason why? Oh,
Oh, multiple questions.
yeah, but they're all assuming that we rejected the null hypothesis.
What?
Because it's saying, how do you explain the conclusion given that listed percentages do not appear to be dramatically different? Well,
Oh well.
I don't have to explain that because we just showed that it's not dramatically different. That's what I get for changing the data, but not changing the question. There is, like I said before, though, there is a way that you could do this where you get the complete opposite outcome, and that would be to actually use the counts. So
Wait, what are the counts?
whatever you would get when you take,
Oh, you mean
that.
so it would be like a population mean thing.
It's still population proportion, but it would be, oh, look at that graph. It would be scaled up significantly. So if I took the 1,424,287 and multiplied it by, this is 7.7%, so 0.077, that would be my count for January. And so whenever you scale up data, the differences between, in this case, observed and expected would be scaled up accordingly. All right. So whatever the difference is between 7.7 and 8 1/3, if we take that and multiply it by 1.4 million, it's going to show a substantial difference from one to the other, which is going to unduly influence the hypothesis test. So what we typically do is scale it down so that the space between values decrease. And so, like that's one of the wishy-washy aspects of the chi-square, is that depending on how you approach it, you could get one conclusion as opposed to the other. But I'm not going to do a follow-up sentence here because my follow-up questions don't make any sense. So I'm just going to say, well, like verbally, I'm not going to write this, that this is telling us that we're not seeing a difference in violent crime rate throughout the year.
We support the claim.
We support the claim. Yeah. So I guess I could write that.
You say ergo.
You can try.
How do you spell that?
ERGO.
Yeah.